A rotating plank starts from rest and has an 18 Newton force applied to the edge of it and will cause it to start to move. And our job is to find the angular acceleration initially for this and then the angular velocity after 3 seconds. Well, the moment of inertia for a plank like this, rotating about a center, so I has a different equation. It is 1/12 m multiplied by the length of the plank squared. So we want to start out by finding the I for this. So I, or the moment of inertia, I equals 1/12. The mass is 5.5, and the length is 3.6 squared. So the I value for this is 5.94 kilogram meters squared. Our first question is to find the value of the angular acceleration. So we're all going to use the equation torque equals I alpha. So our torque, 18 newtons. Now we need to find the point of rotation here. Well, that's half of the length of this. So that would be 1.8. So force times our distance to the point of rotation. That's going to equal I alpha, which is 5.94, multiplied by alpha. And it turns out the angular acceleration is 5.45 rads per second squared. Now the value of the force only lasts for 3 seconds. We can find out the value of the angular velocity after 3 seconds. We'll say omega 2 equals 0, starting from rest, plus our angular acceleration, 5.45, multiplied by the 3-second duration that the acceleration is going through. So omega 2 is then equal to 16.4 rads per second. Now, a bowling pin, for some reason, falls and lands right on there. We'll ignore any effect due to momentum or anything like that and just pretend it lands right there and doesn't bring any velocity with it. But it does bring a value of moment of inertia. It increases the Planck's moment of inertia, and it'll be a point mass since its whole self is rotating around something else, and that would be I equals mr squared. So the I for this is going to equal 1.4. which is number of kilograms, multiplied by its distance to the point of rotation, 1.2 squared. And the I for this is going to be 2.02 kilogram meters squared. Now it's our job to find the new angular velocity once we increase the moment of inertia of this. So we do expect this to slow down. 16.4 rads per second then, okay, will be our beginning velocity as we use the equation I1 omega 1 equals I2 omega 2. Okay, so let's get started on that. Okay, I1 is going to be our 5.94. Omega 1 will be 16.4, because that's how fast it's going when the bowling pin lands on there. Equals now I2, we're going to have to take the 5.94 plus the 2.02 and multiply that by omega 2, which we don't know. Omega 2 is 12.2 radians per second. And as expected, the angular velocity has decreased because the bowling pin has landed and increased the moment of inertia of the rotating system. Awesome.